In this presentation, we're going to focus on fluids, and specifically we're going to talk about density, because density is the important aspect of a fluid when we talk about what happens when we place an object in a fluid, or what effect a fluid can have on its environment. So some of the previous topics that are going to be important in our discussion of fluids is the idea of force. And of course, a force is just a push or a pull. And we are going to use Newton's second law of motion, F equals ma, in our discussion of fluids eventually. Mass is also going to be an important property that we talk about again, and mass, of course, is just an inherent property of all matter, and it's just a measure of how much matter we actually have. It's also a measure of an object's inertia, and of course inertia is the tendency of an object to want to remain in the state of motion that it's in. So more mass means that an object has more inertia, has more tendency to remain in the state that it's in. And then the other topic that we're going to have to use again is weight. And weight is just the force of gravity that acts on an object, and it does depend on the location that you're at, whether you're on the Earth or the Moon. The force of gravity is different on different celestial objects. The other topic that is important for us to remember is that there are different phases of matter, and of course this is something we learn in elementary school, that a material can be in a phase of solid, liquid, or gas. So as we talk about fluids, fluids are basically defined as materials that have the ability to flow. So in terms of the phases of matter, the two phases that have the ability to flow would be liquids. So here's a picture, just a pretty picture of basically a water droplet. And so water is, of course, a liquid. And then we could also have gases. They have the ability to flow as well. There's lots of gases that we could talk about. Air is obviously a gas. This is just a picture of sort of space and some gases in space. So mostly we're going to focus on liquids as we talk about fluids, but we want to keep in mind that, that gases are also considered fluids as well. So one of the important aspects of a fluid that will come into play quite often is the fluid's density. And so density is basically a measure of a material's compactness. So if you can take a lot of material and fit it in a small space, it's very compact, it's very dense. So more specifically, in terms of an equation, density is the mass per unit volume. In physics, for density, we use the symbol rho, and then, of course, for mass, we use m, and for volume, we use capital V. In terms of units that we use for these properties, in physics, the standard unit for mass is kilogram, and the standard unit for length is meters, and so volume is essentially length times length times length, right? Different lengths, but so it would be units of meters times meters times meters, which is meters cubed. So the standard physics unit for density would be mass, kilograms, divided by volume, meters cubed. So this is the standard unit that we would use for density. But you'll notice that there's another unit here associated with density. So because oftentimes we're using with small sample sizes, meaning they have a small volume and they have a small mass, another unit that is very typical would be to use units of mass in grams, volume in centimeters cubed, and then we would have density in grams per centimeter cubed. Now, as we go through this discussion, I'll make sure to identify which sets of units that we're going to use, and also how you can basically go between those different units. So we have this relationship between the density of an object, its mass, and its volume. So we've defined density as the mass per unit volume. Oftentimes, though, we're interested in knowing for a particular material that has a given volume, what is its mass? And so we could rearrange this expression that defines density in terms of mass and volume. By multiplying both sides of this equation by volume, we could solve for the mass, and the mass would just be the density times the volume. As I look at this expression here, the second expression, I realize that maybe I want to know the volume of an object that has a given density and a given mass. So if I take this expression and I divide both sides by density, I get the volume of an object is its mass divided by its density. So these are all the same equation, just rearranged in such a way that we can solve for different variables. And so sometimes, for whatever reason, using this fraction here gives people some difficulty, so we now have it written to solve for each of the possible variables in terms of the other two variables. So here we have a list of, it's a table that has a number of different densities. So let's start with the gases, right? So here are the gases, and the first column here is the density of the gas in grams per centimeter cubed, and this is in kilograms per meter cubed. But as we look at the numbers, let's look at the, well, let's look at these numbers, grams per centimeter cubes. So this is all densities of gases. These appear to be very, very small numbers. So gases have very small densities. Next we can go and we can look at liquids. So here's liquids. Again, this column here is grams per centimeter cubed. This is kilograms per meter cubed. So let's ignore mercury for the moment, and then let's look at the other liquids that we have here, right? So for example, water at 4 degrees Celsius has a density of 1 compared to air. Let's just say air at 0 degrees Celsius is 0.00129. So water is more dense, more compact than air. And in general, the density of liquids is greater than the density of gases. And as we continue down and we look at solids, you can see that the density of the solids in general, let's ignore the ice for the moment, but in general, the density of the solids are larger than the density of the liquids, notwithstanding mercury. Mercury is kind of the exception to the rule. Mercury is extremely dense. So mercury is actually more dense than some of the solids down here. Like mercury has a density of 13.6. It's actually more dense than lead, right? Which is really kind of amazing because we think about lead as being a very dense material. So in general, the materials that are the most dense are solids, in general terms, then followed by liquids, and then the least dense materials would be gases. The other thing I wanted to point out is if we compare the density in grams per centimeter cubed to kilograms per meter cubed, if you look at these, the difference between these is a factor of 1,000. So the easiest one, of course, to look at is water. The density of water is 1 gram per centimeter cubed or 1,000 kilograms per meter cubed. So we can always convert between grams per centimeter cubed and kilograms per meter cubed because it's just a matter of 1,000 in terms of them being different from one another. So in general, the density of a solid is greater than the density of a liquid, and that is greater than the density of a gas, right? So density is basically related to the molecular structure of the substance. So what do we know about solids? We know that solids are made up of molecules, and that in solids, those molecules are very tightly bound together. They can't, they basically are stuck in space, right, in place, and they can't move around a whole lot. So, so I have these 3 containers. The 3 containers all have the same volume, but you look at the solid, and there's a lot more molecules of that solid in that space. It's more compact. It has a higher density. So here's the density of aluminum, steel, and uranium, right? Very dense. Liquids, on the other hand, are not as tightly bound. So they have the ability to, the molecules of those liquids have the ability to sort of break free from one, from a set of molecules and move on to another set. So they're more loosely bound, right? So here some of them are tied together, but then some of them are more loose. Like this molecule right here is not tightly bound to the ones around it. And so there's more space between those molecules. And so a liquid is less dense than a solid in general because of the fact that it's not as compact, right? There's more space between them. And then when you get to a gas, of course, gases are the least bound together in terms of their molecules. The molecules are very free to move around, and so there's even more space between those molecules, and so they are even less compact, and so the density is even less. So this gives us more of a visual representation of the difference between solids, liquids, and gases, and the reason that the densities are the way that they are is related to the molecular structure and how those molecules are bound together. So let's examine a couple of these quick questions to see if we have a good understanding of what's going on. So which has a greater density, 1 kilogram of water or 10 kilograms of water? So the first thing you might look at this question, you might say, all right, well, I've got 1 kilogram of water, I've got 10 kilograms of water. So 10 kilograms of water is obviously more water, but does that mean that it has a greater density? And the answer to that is no. Both 1 kilogram of water and 10 kilograms of water both have exactly the same density because density is a measure of the mass per unit volume. So yes, 10 kilograms of water is more mass, but it also takes up more space, and so it has more volume, but the ratio of the mass per unit volume is the same. So the key is that both of these are water. And so water has a particular density. The density of water is 1 gram per centimeter cubed or 1,000 kilograms per meter cubed. Same material always has the same density. Okay, so we have another question. Which has a greater density, 5 kilograms of lead or 10 kilograms of aluminum? So again, we go back to this idea. We can't just focus on the numbers that are out front because that's the mass. It's not the density. So what we have to do is we have to look at the fact that we are comparing the density of lead and aluminum. So I've put the table here, similar table from the previous page, and I can identify in my table lead and I can identify aluminum, and their densities are given in terms of grams per centimeter cubed. So lead has a larger density than aluminum. So my answer here would be 5 kilograms of lead has a greater density than 10 kilograms of aluminum. And honestly, I don't even need those masses in there. I could have just asked the question, which has a greater density, lead or aluminum? So those numbers that are placed out front are really just designed to sort of throw you off. And so you have to think about that and think about what each of those different quantities represent. Which has a greater density, an entire candy bar or half of a candy bar? So the entire candy bar has a particular volume. Half of the candy bar has half of the volume, but it's a particular type of candy bar. So just like with water has a particular density, the candy bar has a particular density. So both the entire candy bar and half the candy bar have the same density because they're made of a particular material, and materials have a given density. So the entire candy bar has a bigger volume and a bigger mass. Half the candy bar has half the volume, but also half the mass. This one is always a little confusing for people, I think, but what happens to the density of a marshmallow when you squeeze it between your fingers? A loaf of bread works the same way, or a slice of bread. So I always think about my kids when they were really little, they would take a piece of bread and they would like squeeze it down into a ball and then they would want to eat it that way. I always thought that was disgusting, but it's the same idea here. So if you squeeze a marshmallow or you squeeze a piece of bread, you're not changing the mass, right? So the mass is staying the same, but you are changing the volume because you're making that material more compact, right? So the mass is staying the same, but the volume is decreasing when you squeeze it. And so as the volume of the marshmallow decreases, the density increases. So volume is on the bottom, it's getting smaller, and as that gets smaller, the whole fraction gets bigger, and so the density would actually increase as you squeeze it. So what are you doing? You're making it more compact. If you think about the slice of bread, all the little air molecules that are, inside the bread, you're taking those out when you squeeze them, and you're taking all of the actual bread and squishing it down and making it more compact, more dense. Let's consider another example. Suppose that I am given that the density of copper is 8.9 grams per centimeter cubed and the density of silver is 10.5 grams per centimeter cubed. If I take equal volumes of copper and silver and I place them on a scale, which scale is going to read a larger mass? So we have to think about this first from a conceptual standpoint. Silver has a larger density than copper, which means that it's more compact. So if I have equal volumes of copper and silver, there's going to be more mass of silver in that particular volume because it's more compact as compared to the copper. So let's see if we can also think about this from the standpoint of just using some general math expressions. So since density measures compactness, of course the object of the larger density can fit more mass in that given volume as compared to the smaller density. But if we go back and we look at how density, mass, and volume are related to one another, we know that the mass of a substance is just the density of that substance times its volume. Now, we're taking equal volumes of both of these substances, so the volume is the same, but the densities are different. Now, let's just go ahead and pick a particular volume, and we can do that when we're making comparisons. So let's assume a very easy volume of 1 centimeter cubed. And let's determine in 1 centimeter cubed how much mass of silver do I have and how much mass of copper. So the mass of the copper would be the density of copper, 8.9 grams per centimeter cubed, times this volume of copper, which is just 1 centimeter cubed, and I get 8.9 grams. And if I do the same thing for silver, its density is 10.5 times 1 centimeter cubed, I get 10.5 grams. So I have equal volumes of both of these substances, and I find that silver has a greater mass, and thus if we put these both on the scale, these same volumes, silver would have a larger mass reading. So when you think about these density values, you can think about them as the amount of mass per unit volume. So if you have a set volume in 1 centimeter cubed, copper is going to have a mass of 8.9, silver would have a mass of 10.5. So if you had 2 centimeters cubed of copper, it would be double the mass, and so on. So it's a way that you can think about density in terms of volume. So that number out front is going to give you the mass for a given unit of volume. All right, let's put some numbers in and try to calculate some different quantities. Suppose I have a certain piece of metal that has a mass of 125 grams and a volume of 25 centimeters cubed. So somehow I've measured the mass and the volume. And I want to answer the following 3 questions. What's going to be the mass of a single centimeter cubed of this metal? So I have 25 centimeters cubed. What if I want to know the mass of just a single centimeter cubed? What is going to be the volume if I take 800 grams of the metal? And what's the mass of a volume that is 40 centimeters cubed? So we're going to do these in steps, but the first thing I want to look at is for this particular material, I know from the start that it has a mass of 125 grams when the volume is measured to be 25 centimeters cubed. In each of these questions, it's exactly the same metal, which means that the density is going to be the same in all of those cases. So let's go ahead and calculate the density of the metal given its mass and its volume. So the mass is 125, the volume is 25 centimeters cubed, and so I know that this particular metal has a density of 5 grams per centimeter cubed, and that's going to be true regardless of which one of these questions that I am answering. So I've put at the top that the density of this particular metal is 5 grams per centimeter cubed. Now I want to know what is the mass of a single centimeter cubed of this metal. Well, if I look at this expression, I actually can answer that question without doing a whole lot of work. The density is 5 grams for every centimeter cubed. So that means that the mass of a single centimeter cubed has got to be 5 grams. But let's go ahead and let's plug this in. So piece of material 2. I want to know what the mass is. What is the mass? And I know this, I know 1 centimeter cubed. So I know the volume is 1 centimeter cubed. So I can go to my relationship between mass, density, and volume. And I know the mass is the density times the volume. The density is 5 grams per centimeter cubed. The volume is, of course, 1 centimeter cubed. So I get a single centimeter cubed of this particular material is just 5 grams. That should make sense to some extent, just from the basic definition of density. And of course, I would expect my number to be much less than 125 grams, because 125 grams is the mass when I have 25 centimeters cubed. All right, what is the volume of 80 grams of this metal? All right, so again, it's the same metal, so the density is the same. If I think about what's going on, I only have 80 grams. Before I had 125 grams. So I would expect that my volume for 80 grams is going to be less than 25 centimeters cubed. So let's go ahead and put in what we know. We know that the mass of this particular piece of material is 80 grams. We want to know what the volume is, and of course we know the density. So we can solve for the volume. It's just the mass over the density. Our mass is 80 grams, our density is 5, and so we get that the volume is 16 centimeters cubed, which of course is less than 25, and that should make sense. Finally, we want to know what is the mass of 40 centimeters cubed of this metal. Well, this is the volume, 40 centimeters cubed. 40 centimeters cubed is larger than 25 centimeters cubed, so I expect that my mass has to be larger than 125 grams, because when I had 25 centimeters cubed, I had a mass of 125 grams. But let's go ahead and see what happens. So the mass of this particular piece of the material is unknown. The volume is 40 centimeters cubed. And I want to determine what the mass is. So the mass is the density times the volume. The density is still 5, and the volume is 40 centimeters cubed. So I get a mass of 200 grams. So in this particular example, we can see that for a given substance, the density stayed the same in each case, and that for different volumes, I could calculate what the mass was, and also given the mass, I could calculate what the volume is. So this is just an example of how we can use this relationship between density and mass and volume. I wanted to point out that there are other units of volume, and we probably, for the most part, won't use most of these, but anything that has length times length times length, where those lengths, of course, don't all have to be the same size. But so, of course, we've talked about centimeters cubed because we've used that before. It's sometimes written as cc's, or cubic centimeters. And one place that we use this is actually in milliliters. So a cc, or a cubic centimeter, is the same thing as a milliliter. Liters, of course, then is another unit of volume. So 1 liter is equivalent to 1,000 milliliters. So when we talk about volume in terms of liters, that's actually, sometimes drinks, right, are in units of liters. Gallons, right, you get a gallon of milk, that's a volume of the milk. Other ones that we will sometimes see would be teaspoons or tablespoons, that's a matter of volume. And then cubic feet is sometimes used, length times length times length, feet times feet times feet would be feet cubed. One thing that I did want to point out is that another unit of density that we will sometimes use, we've talked about the fact that we can use grams per centimeter cubed for density, but a single gram per centimeter cubed is equivalent to a kilogram per liter. So those are exactly the same density units. And we're going to see that in some of the simulations that we're going to look at. So our last example here is related to just the way we might solve a problem. So I have a merchant at a local flea market, and he sells you a 500 gram solid silver plate. And you can pretty easily measure the mass of the plate. You could just put it on a scale and you measure its mass to be 500 grams. When you get home, you're worried that the merchant has swindled you. How could you determine if the plate is made of pure silver? So you really have two options. The first option is we could look up the density of silver and determine what the volume of the plate should be, and then we could measure the volume to see if that agrees. So we look up the density of silver, we say, all right, well, what should the volume of this particular plate be? And then we try to measure it. Or we could just measure the volume of the plate, and then we could calculate its density. So we would have its mass and its volume. We could calculate the density and then compare it to the known value of silver. But both of these require that we look up the known value of silver so we have some comparison. The issue that we run into is measuring the volume of something that has an irregular shape associated with it. So this silver plate, maybe it's kind of ornate and it has handles and it has something else on it. So it's not like a cube where you can just say, oh, well, I can measure the length times width times height and I can calculate the volume. So under those circumstances, we have to find another way to actually measure the volume. So I'm going to show that in a second, but before I do that, let's just do a quick calculation. Well, yeah, let's do the quick calculation first, and then we can go back and we can see how we would measure the volume. So you notice here that there is there's a link, and that's going to take us to one of the PhET simulations. So let's suppose that we did have a way of measuring the volume. So we look up the density of the silver, and we find the density of silver to be 10.5 grams per centimeter cubed, and we want to calculate what the volume should be for this particular plate, and then we're going to measure the volume and see if it agrees. So the mass of the silver plate is 500 grams, the density is 10.5 grams per centimeter cubed. So what I would expect that the volume should be 47.6 centimeters cubed. So this is what I expect. If my plate is made of silver, this is the volume that I should actually get, but I have to be able to measure it. So how do we measure the volume? So let's consider using the PhET simulation to see if we can measure the volume of an object. So one way that we can do that is by having a container with a fluid and knowing the volume of that particular fluid. So in this particular PhET simulation, it's the density PhET simulation that's available online, and it has, the water in here has a volume of 100 liters. So if I take one of these blocks and I want to measure the volume of the block, I realize that as I place the block in the fluid, the volume of the fluid changes. And so we can watch it change over on the right. And so when the volume of the block is completely submerged in the fluid volume is now reading a different value. And it turns out that the fluid, the water, had to make space for this particular volume of the block. And so whatever the new reading is on the water level, if I look at how it changed, I can determine the volume of the object. So it was at 100 liters, now it's at 101 liters. So the volume of this block is exactly 1 liter. So essentially, I could always measure the volume of an object, specifically our unknown silver plate. I could take it, and if I had a particular volume of water, and I could place it in that water, and I saw how the volume of that water changed, that would tell me the volume of the object. So if I take, for example, I have a larger block A here is larger than block E, and as I place it in the fluid, again, slowly the volume of the fluid changes. Eventually, when the block is completely submerged, the volume reads 103.38 liters. So the volume of this block is 3.38 liters. So that gives us a way of measuring the volume of something that is an unknown object. Now, obviously, these are blocks, so if I measured length times width times height, I could calculate the volume, but if it had a weird shape, it would be more difficult. I wanted to point out that block B appears to be the same volume as block E, right? They're basically the same size. And so let's see what happens when I put block B in. It should read the same volume as block E. So if I just let it go, Block B actually floats. And so the volume that's being read here is not the whole volume of this object. It's only the volume that's underneath the water. So if I have something that floats, I have to grab it and pull it under the water to make sure, and I have to hold it there to make sure that the whole object is completely submerged. So I'm measuring the whole volume of the object. And I notice that on the right it's reading 101 liters. So the volume of block B is also 1 liter. So objects that float, you do have to be a little bit careful. I imagine one of these blocks also floats. There we go. Yeah, so that one floats. So I would need to pull that one under as well. And when I do, it's exactly the same volume as block A was, right? But when I just put it on there, it's floating. I have to pull it under. So the volume here is always measuring the volume that's submerged, right? So the more that I place the object in the water, the more volume that is submerged.